Okay, so I finally made the washing machine drum fire pit. So like it was maybe 3 years ago, we had a problem with our washing machine and it was under a year old. So luckily it was under warranty, but the repair person came and they had took out this drum, and then put a new one in thinking that was a problem. It wasn't the problem, but they found out it was the computer panel. But the drum, when he took it out, I go, "Oh, can I keep it?" And he's like, "Sure." And because I saw this once when I was camping, someone brought one of these, and it works so good as a fire pit because it's got all the little holes in the side that oxygen and air can come in to burn the wood. And there's little holes in the bottom too. So it's surrounded by oxygen. So it's got more oxygen to burn up the wood fuel. So it's some chemistry behind it, but it burns really good. This is barely any wood. There's just like some little bit of wood, and it burns good. So it's like a cleaner burn, more complete combustion, less smoke, and the heat makes the little bit of smoke that's made rise up, so you can get close and warm without smoke in your face. Like after you light it, you're not all smoky like sometimes. But yeah, and I was gonna make it for years. I was gonna make like a fancy metal feet on it and all this. And then Nick, the other day, he was like messing around. He saw a cigarette lighter and he was trying to light little twigs and leaves on fire, being a little pyro like I was. So I go, "Oh, I got to put the fire pit together." So I just threw it together really quick and it came out good. I'll make it better maybe one day, but it's better than not using it, right? Okay, so I got an intro, chapter 9, more alcohols and ether. So exam 1 this Saturday, Sunday, we voted and decided we wanted a weekend exam. The window to start the exam is this Saturday, 6 a.m. to Sunday at 6 a.m. So we got a 24-hour window to start it. And once you enter the exam on Canvas, your 5 hours to complete it and load it back to me begins. So get it done within 5 hours.
Is it technically a 4-hour exam?
Yeah, I'm going to try to make it more like a 2-3 hour exam. I don't want to make it too long.
I was going to say they typically take me a little while longer than the stated time.
I'll try to, that's why I made it 5. So I'll try to make it similar to previous exams, but now you have a little more time to turn it in. And then, within the exam, I'll have a Zoom link for you to join a Zoom video meeting. And I'm going to see how this goes. This is the first time. I'm sure there's going to be plenty of people who are like, "Oh, my camera didn't work," or this or that. Don't stress yourself out and think like, "Oh, I failed the test." No, I understand. Things are going to happen. I'm just going to try to do this, see how it goes. And if it works out okay, I'll keep doing it. And if not, maybe we'll find something different. So what I want you to do is you start your Zoom meeting up and then mute your volume, but keep your video on, and then take your exam in front of your camera. You could have a printed out exam and be just writing on it like that, or you could be using a tablet, whatever you want, just kind of hang out by your camera. If your computer doesn't have a webcam, you could try using your cell phone and just have it plugged into power and pointed towards you. And when you have to get up to use the restroom or something, go ahead. You don't have to ask permission. Just, I get it. If you're like, someone's cheating and they leave for like half an hour and come back, that kind of looks suspect. So don't do that. But I understand if you got to get up, get a drink of water and this and that. Yeah, so I don't expect perfect. We'll do our best, and email me if you have questions, and we'll just see. It's not something that's going to make you fail if you don't do it, but I want you to try to do it. And if you can't do it, let me know why, and we'll try to overcome that for future exams. I know the college has resources. If you don't have like a webcam, we can get you one. And I know I'm not really giving you enough time for this exam. It's just this whole like trying to curb cheating. It's very important to me and it bugs me too much, but I want to spend more effort on teaching those who don't want to cheat. So that's why I didn't put as much time into trying to practice this and everything, but it will. And don't cheat. So that means don't use anything or anyone but the exam. So like I'm going to list some things that are going to be on. There's going to be mechanisms. If you go like, "Oh, I'll just go to the mechanism database and look it up and use that mechanism to try to do this mechanism," that's cheating. Don't do that. Try to practice and learn those mechanisms for yourself. Usually those people who try to cheat don't do as good anyways. And then don't cheat to like copy your friend's exam questions. So like you both have this really strange odd answer, but it's exactly the same. And it's like, probably if I had 1,000 people, one person would do that, but now I have two with the exact same thing. That's odd. So don't do that. All right, so exam one this Saturday, Sunday. Here's the topics. All of my exams are cumulative with emphasis on the most recent material. So for example, last semester we learned about how to draw bond line structures. So that's still part of our things, right? It's just the background now. It's our language. And we'll start, the focus of this exam will be on chapter 18, outcomes 12 and on. Oh, wait, no, chapter 18. Oh no, outcome 18, I'm sorry. Outcome 18 of chapter 8. We started this semester, outcome 18 of our, I didn't really write that right. Outcome 18 of chapter 8. Yeah, there we go. Of our outcomes. And then today we'll get past outcome 12 in chapter 9, but I'll just test you on exam 1 up to outcome 12. We will not finish chapter 9 before the exam, but you should still be working on the homework for chapter 9. So since we're not finishing chapter 9 today, I can't assign the due date for the homework, but I don't want you to think that means, oh, I shouldn't start chapter 9 homework. No, you should do it, for example, after today's lecture, or maybe, yeah, you should be able to do questions 1 through 12 and 20 and 21 on chapter 9. 20 and 21 are spectroscopy ones, so it'll be good practice for you. You'll be asked to draw lots of mechanisms with colors for the reacting electrons, so practice all of them. So you just go through from the chapter 18, outcome 18 of chapter 8. Whenever you see an outcome that says, know this mechanism, practice it a couple times and then go on to the next one. And I'll have a roadmap type problems, kind of like the ones from chapter 8 homework. Number 13, it's a roadmap problem. What I mean is where I start with, say, an alkane, then I say brominate with light, and what do you get? And then that box, you fill it in. Now add magnesium, what do you get? Fill that box in. Now you add an aldehyde, what do you get? Like kind of fill in the blanks, overall reactions. I like those ones. And then I'll have a couple retros at least, maybe 3, but probably just 2, probably like one easier one and then one a little more challenging. And then I'll have spectroscopy questions that include mass spec. Like last semester when I gave you the multiple spectrum problems, I gave you the molecular formula. Now I'll just give you the mass spectrum and you'll derive the molecular formula and show your rule of 13 calculation. So you probably want to practice a rule of 13 calculation, just make sure you're good and ready for that. And then also I might give like a mass spec fragmentation mechanism as well. We'll see. As I'm writing the exam, I haven't written it yet. When I write it, if I'm like, I'll write the exam and then I'll realize it's kind of long. I'll take out a couple questions and so let's see what actually turns up. I'll probably have you answer a nomenclature question. I usually have like one, and it's basically it's pretty obvious. It should be like, what did we just recently learn in nomenclature? We just learned recently, last lecture, how to name ethers, so it'll probably be an ether question. But we did learn alcohol nomenclature, but we did that in 12A. So I probably would ask the ether one, kind of next chapter after 9, we're going to go to 11 alkanes. So, not alkanes, alkenes. So for exam 2, you'd probably expect a question of nomenclature on alkenes, stuff like that. All right, so practice, 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 practice. And I gave you these helpful tips last time, things to practice. Was there a question?
I have a quick question.
Mm-hmm.
So if we, on Saturday, if we go to the restroom, since we leave like the computer or our phone on the desk, should we turn off the camera or should we leave it on, like on the desk while we go like to a different room, or should we turn it off, or does it not matter?
I would just leave it on and just leave it in that room. Did you mean like you were going to take your phone into the other room? If that was your camera?
No, I meant like, yeah, just leave it on the desk where we were working while we go to the other room. That
sounds good.
Okay.
Yep. Just like in a normal setting at campus, students during exams say, use your restroom. Okay. Okay, and then I'll set up, this was an idea I got from maybe Stephanie. I thought this was a good idea. I think this is going to work out good. I set up the following Zoom study session. So, and I'll check in from time to time. You'll see it's long. I'm not going to be the whole time. But and you can help each other. You can go there. So it'll be on this Thursday tomorrow, after office hours tomorrow. You can go there, and it'll be available. The Zoom will be available from right after noon, 12:05 p.m. to 11:05 p.m. So like a long, like what is that, 11 hours. So you can come in, check in there. If you're studying and you have a question, you might see a classmate on there like, oh, do you know how to do this? Can you help me with this? Or blah, blah, blah. Or just go on there if you're bored and tired of studying. You can go on there. Anybody want me to help with anything? Because I'm sick of studying on my own. So go in there. And besides the Zoom that will be running, and I'm assuming the Zoom will work for 11 hours straight. It's not going to be recorded, so I think it'll work. If not, I'll check in every once in a while too. I also made a Jamboard for this Thursday session, so you could, when you're on the Zoom, you can go as whoever's there. If there's 4 or 5 of you, you're like, oh yeah, hey, let's try working out that problem on this Jamboard. And then I did the same thing for Friday. So this is tomorrow and Friday. You could check in there. And let's say you check in and like no one's there, and you're like you're like just studying and you have the Zoom going in the background, no one's there, no one there. You can write a little note and say, hey, if anybody winds up coming, email me and I'll come join you or something. You know, you can type little notes to each other on the Jamboard. Same for Friday. And then next Monday, I won't have an office hour because I have this red tape meeting where I gotta go talk about, I made changes to my curriculum because we're online now. And so they have to like, oh, I thought it was all done, but now they're like, oh, we have a meeting to make sure the changes in the curriculum are okay. So it transfers to the Davis or Sac State order. I'm like, okay, whatever. So I have a meeting on Monday, so no office hour, but I figured that one might be, I mean, I like to always have office hours, but that one's the day after the exam, but it's going to be after a lecture too, but that's okay. We'll meet Tuesday next week, like normal. Okay, any questions about that?
I have a quick question.
Yeah.
For the test, are we allowed to use our phone at the end to take pictures and upload it?
Yeah, that's fine.
Okay, thank you.
Yeah, just maybe, yeah, I guess if you're using your phone for your Zoom, you mean, right?
No.
Oh, I thought yeah, you could definitely use your phone to take pictures of the exam to make your file to submit. Yep.
Okay.
What's that?
If we are using our phone for Zoom,
yeah, you could like stop the Zoom on your phone, take the pictures of it and submit it. And I'll be able to tell, like, if someone stops their Zoom on their phone and then they don't turn the exam in for 4 hours, it's kind of obvious they're probably getting help from some of them. So,
yeah.
But I mean, if it's like, yeah. And once again, I feel like the people who are asking these questions aren't going to cheat, but it's like, oh, it sucks. It's all about trying to avoid this. Who will cheat? You know?
Because I'm also trying to think about how I'll do it. Because I print off my phone because that's easier connected to the printer off Wi-Fi than the computer for some reason. So I'm just trying to see how to run that, and then.
Oh, don't worry about it. If you have to use your phone to print it and you're not on Zoom yet, are you going to use your phone for the camera for Zoom?
I might. I'm still debating because I like to have, because I print black and white, so I like to have the actual exam open on the computer.
Yeah, that's fine.
And then, but I need to print it off my phone because that's
fine.
One that's
so
connected.
Like you can have Zoom recording you from your computer, and while it's recording you from your computer, you can go online and look at the exam in color. It'll still record your face. So like right now, I'm on a Jamboard online, right? But you can still see me.
Okay.
Yeah.
Perfect.
So you can be like, you can still just cheat. You can go online and look up stuff, you know, like, but I don't know, at least I don't see someone sitting next to you. Yeah, I don't know if this is really helping much at all with cheating, but we'll see. I'm trying it out. Yeah, it's just the world we live in. And so, yeah, sorry, Elago said you asked about homework keys. I won't have time to make homework keys, but you can, you know, ask in office hour and email me if you have like, oh, this particular one, what's going on? I've already answered some homework and workshop questions in office hours, so they're in their Jamboards. All right. I wish I had homework keys, but I just haven't had time. And I made up these homeworks the last two. I spent a lot of time on the last two homeworks. I really changed them up. Every year I change them up a little bit, but this year I changed them a lot, which is good. But that means I didn't have time to make a key, but that's right. All right. Any other questions? Yeah.
Can you guys hear me? Oh, okay. Because I don't know.
I can hear you now.
My internet's a little too big. It's because like I don't know which questions I got wrong because I was doing the homework, but I felt like some of them wasn't right.
Mhm. I know in a perfect world, I would have a key for you, Elagosa, but I feel like currently my job, the way I want to do it perfect would require like 3 times as many hours in a day. And that's, so I just got to triage and do the best I can with, but I feel like there's so much learning going on right now. It's actually working well. Like I think I'm doing well as a teacher, even though I'm not getting,
Yeah, definitely.
I'm getting a
doing lot.
third as much done as I want, but still there's so much learning. It's good. It'll get better, more experience.
I'm telling you, we could write the key ourselves as students and just like put it
Yeah,
on.
you can, yeah. So Elagosa, you can like, if you have like a question on the homework in the study session tomorrow, you can, throw up some of the questions you're less confident on. Say, what do you guys think? That'd be a good way to help each other study.
Yeah, I think I'm gonna do that.
Yeah, Demery, I didn't set up, Demery's asking about discussion boards for specific chapters. Last semester, I don't know, I never got alerted for the discussion boards. And I felt like when I would go to the discussion boards, it would take me forever to answer stuff. And it was one of those things where I didn't feel like it was as good for me as a teacher. Like it wasn't the best use of time with the limited time I have. So yeah, I don't have the chapter discussion things set up. I can think about it after this first exam if you wanna, if you thought those were really useful. I do have, though, let me get out of this here. Yeah, I'm all done with this. So I do have on our Google Sheets, organic chem step by step. I do have like in our office hour descriptions, things like this office hour on the second week, Monday, we did electrophile, nucleophile strength, oxidation reduction. So you can kind of look in there for stuff. So the office hours are sort of like, serve as that purpose of that discussion board chapter questions, sort of. Yeah. Okay. So let's get back to chapter 9. We ended off here. We did some Williamson ether synthesis. And I got my Jamboard set up for today. Oh, whoops. I was charging my iPad. That wasn't good. I'm going to do a quick, one more Williamson ether synthesis to review that for you. Yep. So Williamson ether synthesis. What reaction mechanism does it undergo? Is it
SN2?
that's right, it's SN2. And is it run under acidic or basic conditions?
Acidic?
Basic conditions. Because remember, the alkoxides, the RO minus, it's basically like, I don't like that minus RO. It's basically like hydroxide, like sodium hydroxide, right? Like that, right? So when you see an alkoxide, think, why am I doing it this way? This is ugly. Got my iPad right here. So, yeah, it's red and black. Okay, so when you see like ethoxide here, think of it, it's about the same as hydroxide in terms of base strength. STR. Okay, so they're both strong bases. Okay, so the Williamson ether synthesis is a way to make ethers under basic conditions. And then after I do this example, we'll go into the mineral acid synthesis of ethers, which is obviously under acidic conditions. So let's look at a retro. I like this one here. I came up with it earlier. How should we make this guy via Williamson ether synthesis? Should we make it from cleaving here, where I have a leaving group there, primary bromide, and an alpha oxide, a strong base? Or should I try cleaving it here? Not cleaving it, disconnecting it like a retro backwards, and have like a methyl bromide. Which way would be better to do in terms of Williamson ether synthesis?
The bottom one,
Why the, yeah, you're right. Why is that, Jesse?
because the methyl is more available.
Less steric hindrance?
Yeah.
It'll be SN2 major versus E2 major.
That's right. So I've got a primary branched electrophile there, or down here I have a methyl electrophile. The methyl electrophile can actually only undergo SN1. Can't do E2 because it's only got one carbon. Yep, so this one is the better choice. SN2 major. Some steric hindrance for this one. E2 would be major. Oh. Okay, so let me go to the next panel. We'll do the synthesis. Here's our synthesis. Let's start from the alcohol. How can I make this alcohol into an alkoxide?
Deprotonate it first.
Yeah, I need something to deprotonate it. Let's look really quick back at chapter 9 outcomes. Number 1, we can use LDA, lithium disulfide, to deprotonate it, make the alkoxide, or an organometallic, potassium hydride, sodium, or alkali metals. Jesse, which one would you like to use? Any of these are fine.
NaNH2.
Sodium amide, it is. Oops. Yeah, switch my So that's sodium amide, sodium plus NH2 minus. So this is just straight acid base. And it's a very product favored reaction because the ammonia that's formed is a weaker acid than the alcohol initially. So this guy is, that's ugly. This one is got a pKa equal to about 35, where over here, our alcohol is about 16-ish, 15, 16. So yep, that's product favorite. And then we'll take our alkoxide and we'll add our methyl bromide and maybe like DMSO, some good SN2 solvent. And we'll get a good yield of SN2 major. Williamson ether synthesis. All right, so we got that. Next up is the mineral acid synthesis. So in the mineral acid synthesis, the mineral acid refers to generally like sulfuric acid is considered a mineral acid. So we take an alcohol and it could react with itself or another alcohol. In this case, it's reacting with itself. So like two T-butanols are going to come together to make a ditert-butyl ether. So let's work on that one.
Makes it a mineral acid.
I think it's because like sulfur is found in minerals like sulfur, sulfates and things.
Okay.
And there's no carbon in sulfuric acid. So you think of those as like mineral acids. That's
Professor?
Yeah.
For the Williamson ether synthesis, does it matter whether we use methanol or DMSO?
If you use DMSO, your reaction will be faster to produce this ether. If you use, say, like methanol, that wouldn't be as good a choice here. Do you know why methanol would probably not work too good here?
It is SN2, right?
No, it's because of this. If you have methanol, there's going to be an equilibrium of these guys. And the K equilibrium is going to be equal to 10 to the 16 minus 16, 10 to the 0, 1. So you'll have about an equal amount maybe of both. Maybe you would actually have more. You probably have, in a practical sense, you probably have more methoxide than this, because if this is your solvent, it's usually at a much higher concentration. So it'll pretty much make only that. So methanol wouldn't be good in this case, and alcohol solvent wouldn't be good.
Mm.
Good question.
And we also need a solvent for NaNH2, right?
Yeah. Yeah, yeah, we could throw a solvent in there. We want a solvent that's not acidic, not protic. What do you think is going to work? Can you think of a non-protic solvent we use a lot? GHF will be good. GHF or ether, something like that. When you have a very strong base like this, you can't have it in a protic solvent. It would just, if I had to say methanol is my solvent here, that would be bad because it would just deprotonate the solvent. Good question. Okay, so for the mineral acid synthesis, let's see what's going to happen first. This is something I hope you're going to enjoy this. I think you're going to see that the mechanism for this will just make sense to you guys because I've been working really hard and you've been working hard at trying to understand how mechanisms work. So I'll talk you through it and let's see if you can do it. So what do you think the first step of this mechanism is? We have this alcohol and sulfuric acid. What's the reactivity of sulfuric acid?
Strong acid.
Strong acid. And what do they do?
Protonate.
Protonate.
Yeah, someone say it. Someone say it good, like a Geico guy.
Strong acid, you protonate. It's what you do.
There you go.
Wouldn't it be protonate?
Protonate? Oh, did you say deprotonate? Should be that. You you're a strong acid, you protonate. It's what you do. So yeah, this is a very strong acid. So the alcohol, one of the alcohols is going to get protonated. I'm gonna try to do this colorful. How do you guys feel about me using the colors in lecture? Is it still helpful, or is it like we're beyond the colors?
It's still helpful sometimes.
Good.
Especially with like some of the like lithium, aluminum, like hydride, those reactions are a little weird, so it helps.
Yeah, that's true. Is this reaction product favored?
Yes.
Yeah, very product favored, huh? Remember the pKa of,
-10 and -2. So
I think it's like -12. But you know, if you look it up, it depends. Because it's such a strong acid, it's kind of an approximation to the pKa in water. So but it's very strong. So then this one's about -2. Yeah. So product favorite. And if you're a strong acid, you protonate. It's what you do. I should work on my typing. I should do one of those like typing games like what little kids do, where you're like trying to make the frog go across the street by typing the correct letters or something. All right. Also, let's talk about this alcohol. Does it have a good leaving group? Is that alcohol a good leaving group?
No.
No.
Bad leaving group. Bad. Now, what is it though? After it's been protonated.
Good leaving group.
Good leaving group. What? So what's going to happen next?
It's gonna leave.
Yeah, it's also, what kind of electrophile is it?
The water?
So it's got a good leaving group. This is an electrophile now. It's got a good leaving group. And what is it? Is it a methyl, primary, secondary, or tertiary electrophile?
Tertiary?
Yeah, so it could just leave on its own, right? Tertiary carbocations are the most stable. So this water could leave. And we get a tertiary carbocation, and what do we think? Rearrangement. Sneaking up behind you late. Could it happen though? Will it rearrange?
No.
No, it's at the lowest, isn't it?
It's tertiary. All right. So I want to remember now. I want to get to this isopropyl diturbutyl ether here. What do I need to happen? I got tertiary carbocation. What else? What else is in solution that can get me there?
The original alcohol.
Yeah. Another alcohol comes along. What kind of reactivity does this alcohol have? In terms of its basicity and nucleophilicity. Is it a strong or a weak base?
Weak.
Weak base and nucleophile. Both, it's weak both ways, right? But what about a carbocation? What kind of reactivity does it have? It's a very strong electrophile. Super strong. So the weak guy can react with it. It's going to get sucked in there. There we go. We're going to make that bond to make the ether. Are any of you feeling like, yeah, this just makes sense? I got it. There we go. We're almost done. We're almost to this diethyl ether, right? Up here. Almost there. Diethyl, sorry. Diterpetal ether, yeah. So what do you think?
It's gonna get deprotonated by the acid.
Good. Was anybody thinking the hydrogen sulfate would deprotonate it?
I'm taking the water.
Well, the what? Yeah, it could be the water too, actually. But there's going to be more alcohol, especially at the beginning of the reaction. So I'm going to go with the diisopropyl ether, and then because it'll also show you that this mechanism, you don't need a lot of the
Wouldn't the sulfuric
do you?
acid protonate, not deprotonate?
That's right. It's too strong it's such a strong acid, sulfuric acid. That means that its conjugate base is a very weak base. So what a lot of times students will do, and textbooks will show, they'll show this deprotonating, but I don't think happens. I think it's just like they're being lazy. They just want to, I don't know, don't want to have to think about it too much or something. But the thing that's cool about this is because you're doing it correctly, you're using the correct base to deprotonate it. You see that this guy now is ready to continue on, huh? It's a leaving group can leave, right? So how much sulfuric acid do we need to start this to make this reaction work?
A small amount.
Yeah, you don't need an equivalence of the sulfuric acid.
So sulfuric acid isn't a catalyst then?
I don't want to call it a catalyst because catalysts, by definition, they should be regenerated in the reaction.
Right.
And this one's not regenerated. It's just, it's done at this point, right? If it were to be the base to deprotonate, if it were the base that deprotonated this right here, then we could say it's catalyst. And that's why I think a lot of textbooks will show incorrectly this being, and they'll say this is a catalyst, but I don't think it's right. I think I think of it as like the catalytic initiator. Maybe this is the catalyst because it keeps getting regenerated till the end. Nah, because at the end it's not regenerated. So I think, yeah. But you can say, people will say you use a catalytic amount of sulfuric acid, meaning not a full equivalence, but I'll be more specific. I'll say you do not need a full equivalence of sulfuric acid. And yeah, there we go. Not too bad, right?
Not too bad.
Not too bad. So let's do another one, but this time we'll do it mixed. A mixed mineral acid ether synthesis.
Professor?
Yep.
So can this reaction happen with just one molecule of sulfuric acid?
Yes, theoretically. Yeah.
Okay.
So we're going to do this. I'm going to do this now, and then I'm going to show you it later for, we're going to use this sort of thing for protecting groups. So right now you're like, what's a protecting group? But I'm just putting that in your brain for later, where you'll see like when we use protecting groups. So let's make I'm going to make a tert butyl ether out of an alcohol that's not tert butyl. So can you give me an alcohol, like, you know, about 5 carbons or less or so? Anybody got a number?
3.
3? Okay. I'll go like this. I'll make it a primary alcohol. So if I take this primary alcohol and I treat it with T-butanol and sulfuric acid, my major product will be, oops, the following. And then we'll also get HSO4 minus and some leftover like this probably. So that will be my major product. And I'll try to convince you with the mechanism why this one's the major. We will have other minor products, say, for example, when 2 tert butyls come together, or when 2 of these come together, 2 of the propyl ethers. So I'll just draw those off to the side here. Let's say. Okay. Getting a little bit windy today. So, and on the exam, do this for me. It really helps keep things clear. Be good about having, say, the overall reaction. Overall reaction separate from the mechanism. So there's an overall mechanisms down here. Just makes things neater and more understandable. So let's start this reaction off. We've got the 2 alcohols in solution. And sulfuric acid. Could they both be protonated? Yes. It's favorable for both of them to be protonated. And when the alcohols get protonated, they become good leaving groups, right? Same thing over here. Okay. Let's evaluate these 2. So this one is a tertiary electrophile. Good leaving group. The one over here, how would I describe it?
Primary.
Primary electrophile. Good leaving group. Yep. Okay. And we also have, those can be our electrophiles now. And we have alcohols that haven't been protonated that will be our nucleophiles. So I don't want to draw it right there because I want to use this area. I'm trying to figure out the best way to place everything. I don't want to draw my alcohols here. I'll just talk about them up here. What kind of reactivity does this alcohol have? Is it it's not really an electrophile because that's a horrible leaving group, but what is it? In terms of, so
Weak base.
Yep, a weak base / nucleophile, right? And then what about the alcohol up here? Same thing? Yep. Okay, so this guy who's a primary electrophile, can it undergo SN1? That's basically what we saw earlier, right? On the last slide, the mechanism was SN1, leaving group had to leave. Can it do an SN1 step right now and have that good leaving group leave and make a primary carbocation?
No.
No primary carbocation. No SN1. Okay, so but maybe it can undergo SN2 reactions, right? So for instance, to form this product over here, that has to be via an SN2. And what would my nucleophile be? It would have to be this guy, the weak nucleophile. So it would have to do an SN2. Does that seem very product favored, very good reaction? No. So only minor SN2 because of weak alcohol nucleophiles. Because for SN2, you need strong nucleophiles because they have to come in and kick that leaving group out. SN1 is usually weak nucleophiles because it's the carbocation for it to grab onto. That's really electrophilic. All right, so this guy, it can't do SN1, can do SN2, but the nucleophile is weak, so not a lot of SN2 is going to happen. What about this one here? Can it do SN1?
Yes.
Yes to SN1. What about SN2?
No.
No to SN2. Too crowded. Tertiary. Too much steric hindrance. All right, so our major pathway at this point will be to do what? This guy's not going to make a carbocation. It's not going to have much SN2. This one can definitely do tertiary electrophile carbocations and do SN1. So what should I do mechanistically? What's my main pathway at this point?
SN1 on the tertiary electrophile.
That's right, SN1 from here. Oh, let me fix that up. Okay, so now we have this very strong electrophile. So the weak nucleophiles are like, oh yeah, we can react with that. Somebody making tea? Oh no, that's just the wind. It sounds like a teapot. Very strong electrophile. Okay, so now it comes down to our two nucleophiles. Who do you think is a stronger nucleophile? They're pretty similar. They're both alcohols. The difference is the chain. We've got a linear 3-carbon chain, and here we have a branched 1, 2, 3, 4-carbon portion of it. Who's the stronger nucleophile?
Linear,
Yeah, why do you think that is?
less steric hindrance and like less rest of the part of it.
That's right. So here we have it. So versus here, stronger nucleophile. I'm going to say this one's a stronger nucleophile. Actually, I'll move this over. Erase that. And we're going to say this one's stronger. Less steric hindrance. Cool. All right, so next step of the mechanism, what do we do? Add to that carbocation. It's a weak nucleophile. They're both weak nucleophiles, but this one's like less weak. Almost there. What do I do to
Well,
finish it
just
off?
due to the carbocation being a strong, very strong, that's why they can work.
Yeah. So if you have, whenever you have, I try to teach the class in a way, like if you have two strong things, they're going to react. A strong acid, strong base, they react. If you have two weak, they don't react much, or maybe not at all. Like a weak nucleophile, weak electrophile, not going to react much. Weak acid, weak base, don't react much. But if you have one strong, that can help the weak one along. So a very strong acid, say like sulfuric acid, will react with a weak base. And so a very strong electrophile will react with a weak nucleophile. That makes sense?
Thank you.
You're welcome. And then I'm going to finish it off. I'll just deprotonate, and I'll use this guy. I could use either one, actually. Either alcohol. This one, I would think, actually is a little more nucleophilic. Does anybody know why I would, not nucleophilic, I'm sorry, more basic. I think the T-butanol is a little more basic. What's that?
I'm just looking. Oh, okay, I see where the bond, because I was like, you draw a terbutyl on top of the oxygen, but I can see the bond now. Never mind.
No problem. I know it's I kind of ran out of room on here. It's nice to keep mechanisms all on one slide, but sometimes it's just, they get too much. All right. There we go. Are you guys convinced this is the major product? Cool. Even though I didn't hear a yes, I'm assuming I'm visualizing virtual head nods.
You were saying that the T-butanol is, or T-butoxide is a stronger base?
Not T-butoxide, but T-butanol. Yeah.
Okay.
So I'm going to say it's a stronger base because it's got more sp3 carbons close by donating electron density. What do you think? It might be a weaker base. They're pretty close because the conjugate acid might be stronger.
Can I ask a question?
Yeah.
Would that mean that the overall product wouldn't be, or is it both? Would it be both the one with the positive charge and the terbutyl end?
No, I want you to stop at this guy, at the neutral. I'm going to treat this as a reactive intermediate. Is that what you meant?
Oh, no, I meant the one on the very right at the top.
This is a product here?
Yeah.
Oh, yeah. At the very, at the top, I misdrew this, huh? Is this what you're saying?
Oh, yeah.
That's.
I was wondering if it was both of those. Or...
Yeah, I was in error. Thank you. Thank you for pointing it out, John. Yep. All right. And then, so it's pretty nice, huh? I like how chapter 9 has got a lot of review from the old stuff, like Williamson ether synthesis, that's reviewing SN2 versus E2. And now the mineral acid synthesis is an SN1 type of reaction. Pretty nice, huh? Okay, so sulfuric acid would be a better acid to use, even though phosphoric acid is also a mineral acid, because we don't want elimination. When we get to this carbocation right here, we don't want like a stronger base in solution that's going to deprotonate one carbon away. And if you remember, when phosphoric acid gets deprotonated, it has a stronger base than the alcohols and stronger, of course, than the conjugate base of sulfuric. So that works. It's better to have sulfuric over phosphoric here. And then you don't want to heat the reaction too much. Like you just want to keep it cool, because remember, cool favors SN1. If we heat it up, then when we get to this carbocations point here, the alcohol could deprotonate more often one carbon away. I could have drawn over here. There's alkene minor products as well, because a little bit of E1 takes place. All right. So I've got this ether synthesis animation quiz. I'll go through it real quick now to really try to hammer this in. And I have this as part of the chapter 9 homework I want you to do as well. Let's check it out real quick. Yeah, this would be good. And with this one. So ether synthesis, I was looking for a theme for this one. So of course I thought of like the ether drug use, the diethyl ether. So this is from the movie and book Fear and Loathing in Las Vegas. There's nothing more deranged than a man in the depths of an ether binge. So here we go. We got diethyl ether is the one that's abused. And it's also used as an anesthetic, not abused. Has an ethyl group on ether side of the oxygen. So Williamson ether synthesis is SN2. Mineral acid ether synthesis, actually SN2 sometimes as well, like that minor product. I'll show you what I mean by that. So let's look at Williamson ether synthesis first. You'll need an alkoxide, an electrophile that's either methyl or primary and unbranched, and it's SN2 and you get your ether. So this ethanol here, we can make it into the alkoxide, and you can add sodium metal. That's a different way than we saw in lecture, but that works as well. Remember, it generates hydrogen gas. You gotta be careful with that one. We didn't learn that mechanism, but I want you to know that's the very common way to make alkoxides. That's our alkoxide. And then our electrophile, we might add like a primary unbranched one. So we'll get majority SN2. And then there's our ether. And you can see the mechanism. Hopefully you can visualize it in your head already. So that's successful Williamson ether synthesis. You can deprotonate like that, SN2, huh? Done. And then here's another Williamson ether, but this one's an attempt and it fails. What? So the problem with this one, you tell me right when I write it up. What's going to be the problem?
E2 major.
Yep, it's too much crowding. The cone of reactivity for SN2 is very small with a strong base. You're going to get basically E2 as your major, very little SN2. So mechanistically, it's a good old-fashioned E2 reaction. Boom, got my hinge. I'm deprotonating one carbon away. And there we got it. So that one didn't work. So if I wanted to make an ether out of these two, like a 3 carbon on one side, isopropyl on one side and a propyl on the other, a linear propyl, I wouldn't do it via Williamson ether synthesis. I would do it via mineral acid synthesis. So you need an alcohol and another alcohol, could be the same one, mineral acid, you get your ester ether. So in this first one, I'm going to do the one we did in lecture already, huh? Sulfuric acid. And sulfuric acid, you'll see here is a bottle of sulfuric acid. It has a yellow cap. When I was in grad school, my professor would ask us, just kind of goofing around. He'd be like, okay, what bottle has a yellow cap? And you'd go, oh, sulfuric acid. Which one has the brown cap? Oh, acetic acid, orange, nitric acid, concentrated nitric. So that's the yellow. Here we go, mineral acid. So we make that, boom, boom, boom. We saw this already. Let's do it. Let's do it. Alcohol, bad leaving group, bad. Ooh. And then protonate it, very product favored. Good leaving group. Get your, and then now it's tertiary. So you can make cation, super strong, ultra strong electrophile. The weak nucleophile will react. And you deprotonate. Oh, I use water this time. I like water better. Yeah, why did I do water in lecture? Yeah. The water will get protonated eventually. I like this better. I'll accept either answer, like I actually said before, the water or the alcohol. I like both actually. The thing I like about using the water here is that now the water has become hydronium. So it's like we took water out of the reaction, we remove water. So by Le Chatelier's principle, you're getting more products. But in solution, both things are happening. At this point, the alcohol could also deprotonate that. All right, so here's one with mixed alcohols. Oh no, this is an SM2 one, sorry. So bad leaving group, protonate, good leaving group. Now it's primary electrophile. Can we do SN1? Nope. Weak nucleophile, but if there's nothing else around, like if this is all we got, you can get the ether to form. So this is possible to make these. But if this is a secondary or tertiary electrophile, it's going to go via SN1. But if you've got no other option, it could do this. All right, and then on the exam, on the homework, I have you take this quiz. And on the homework questions like this, you'll fill in the answers. I want you to write them in. And then after you write them in, I want you to go back and look at the answer key and grade it, correct it, and then write sentences why you think you missed it. And then turn that in with the homework too. Most people did that, but a few people didn't turn it in. And they're like, oh, I was supposed to turn that in. So yeah, like all the homework questions, turn them in. Okay.
We are on, we've made some ethers under acidic and basic conditions, and now we're going to cleave them under acidic conditions. Ethers are very stable to bases, basic conditions, but they can be cleaved under acidic. And when I show you the reactions, it's going to hopefully just make sense. It's again, our main big four reactions are involved. It's the SN1 or SN2 mechanisms for these. And what we're going to use is we're going to use strong acids, but our strong acids are going to have conjugate bases that are strong nucleophiles. So let's do some examples of that. Oh, I lost my jam. No, this is my Jamboard.
This looks like this is the last, what are those called? The things that are going to be on the exam. Yeah, we're doing 12
this is the
right
last
now.
outcome. Yeah, last outcome for exam 1, but the next outcomes will be exam 2. But actually, and sometimes people might feel like, oh, I don't need to watch the lecture anymore because that stuff's not going to be on exam 1. But when the stuff I talk to you next about, the concepts will be again like SN2, nucleophile, electrophile. So it really can help a lot.
Builds on itself.
Yeah, like for example, I bet if you look back at your exam on SN1, SN2, E1, E2 from last semester, that it'll look a lot easier because what we're doing now is those same ideas we're getting better and better at.
Just refining them.
Yeah. I try to teach the class where it's like everything's connected. Ether cleavage. So the ether cleavages, they need to happen under acidic conditions. With strong acids that have conjugate strong nucleophiles. Okay. Let's cleave the old classic diethyl ether first. The most common ether, diethyl ether, people refer to it as just ether or ethyl ether or ethoxyethane. So we can cleave this with like HBr.
So if you would have given this on an exam, which I doubt you would, but how would you want us to name it? Would you take diethyl ether, or would you want us to do?
I'll say do the IUPAC, which would be the ethoxyethane. If you put diethyl ether, I'd probably be like, sure, that's fine. But ethox.
Yeah, you're not gonna ding us for naming it water instead of dihydrogen monoxide.
Yes, but be very careful with dihydrogen monoxide. That's they find presence of that in all cancer cells. And it's responsible for a lot of deaths every year, that dihydrogen monoxide.
Every single human that's ever died in history has been found to have high concentrations of dihydrogen monoxide in their body.
Very true. It's scary. All right, so we get this and this. Okay, so I'm going to be good. I'm going to keep my overall reaction separate from my mechanism. And so I'm once again hoping that when I go over this mechanism, you're gonna say, oh yeah, that just makes sense. I'm gonna be extra colorful on this one. So the ether is pretty unreactive. It's not a strong base, not a strong nucleophile, but it will, it's a weak base, like similar to an alcohol, probably a little weaker, but it will react with strong acids, right? So this HBr, I guess I'll go yellow on this one. HBr, it's a strong acid, right? So what's it do?
Protonates.
Strong acids protonate. It's, oh man, I wish I could spell. It's IT apostrophe S. It's what they do. So what's it going to protonate on the ether?
The oxygen lone pair.
You got it.
Hold on. It sounds like it's like in a movie or something.
I know. Hold on to Toto.
It sounds like it's about to whisper, think rearrangements.
That's right. Think rearrangements. Okay. So this first step sets everything up because we started off with, you could think of this molecule as having like it's a double-sided electrophile. With two bad leaving groups. Okay. So you can, if I consider this an electrophilic carbon here, then all this is a leaving group. And if that leaving group is bad, it's going to come off as an alkoxide. That would make a negatively charged alkoxide, which is a strong base, bad leaving group. Or I consider this carbon, I can consider this carbon to be my electrophilic carbon. And if a nucleophile attacked there, it would make this bond go there. It would make an alkoxide on the other side, strong base, bad leaving group. So that's what I mean by a double-sided electrophile. It might be attacked here or there. Okay. Is our HBr a nucleophile? No. not a nucleophile. It's strong acid, not a nucleophile. Okay, and now over here, we again have a, well, more so now. Before I called it a double-sided electrophile, but those leaving groups are so bad, maybe we shouldn't even call it an electrophile. But now it's a double-sided electrophile with 2 good leaving groups. Because our a nucleophile can come in and attack this carbon, that make that the electrophilic carbon. This bond breaks and goes here and makes ethanol a weak base, good leaving group. Or a nucleophile can come in and attack this side to break the bond there to make ethanol again, a weak base, good leaving group. So this first step turned our bad leaving group into an electrophile, like to a double-sided. Oh, what I do? I hit a command. I was trying to go command Y.
It's the wind.
Or was it in the list? I was just. Yeah. So we have a double-sided electrophile now with 2 good leaving groups. And what happened to what's the conjugate base of hydrobromic acid? It's a very weak what? Base. Very weak base. And a strong what? So this is one that's interesting in that way, that it's weak one way and strong another. So before this first step of the mechanism, we didn't have a nucleophile. Now we have a strong nucleophile. So this is a double-sided, and I should add something else about this electrophile. What kind of electrophile is it? It won't let me. There it is. It's a primary, double primary electrophile is what I should say, huh? Double. Was that what you were going to say, Stephanie?
Yeah.
Oh, here we go. Option Shift 8. Bam. Thank you, Ryan. Look at that. I got a superscripted 0 there. Oh. So what's going to happen with this one? What's going to happen next to finish this mechanism off?
SN2.
Straight SN2, huh? Easy peasy. I'm gonna call it more of like a forward direction. I don't think it's gonna go back. A lot of colors on this one. Colors, colors. Boom, and the bromide is here. So what do you think? Pretty easy? So we'll try one more, but we'll do a mixed ether. Okay, so I'm gonna make a mixed ether. One side's gonna have a tertiary side, and the other side I'll make it methyl. That can be confusing sometimes. So what do you want on the tertiary side? How many carbons? You want to just go straight 4, make it easy, or add some stereochem?
Let's add stereochem.
Okay, I'll go boop, boop, boop. We'll use hydroiodic acid this time. Switch it up a little bit. So this one is a, what was I gonna say? I don't know what I was gonna type here. Oh, overall reaction. Okay, and maybe we'll do the mechanism first to help us see it before I write out the overall reaction products here. All right, what's the first step of the mechanism?
Protonate.
Yeah, who's gonna protonate what?
The oxygen gets protonated by the hydroiodic acid.
Good. And why will the hydroiodic acid protonate it?
It's a strong acid. It's what it does.
That's what they do. That's right. Okay, now I've got a double-sided electrophile with good leaving group, and I got a nucleophile. So on this side, what kind of electrophile do I have on that side? Is it a methyl primary, secondary, or tertiary?
Tertiary?
Tertiary electrophile. On that side, yeah. So what could that undergo? Could that undergo SN1 and SN2?
Just SN1?
Good. Just SN1.
I'm sorry, which one are you talking about? Oh, where you said tertiary electrophile?
Right here. I'll make it a little closer. That carbon is the electrophilic carbon. And what I'm saying is a nucleophile can come in and like this could be your leaving group and that could make a carbocation. Can you see this happening?
Yeah. Okay. And then it was connected. Oh, it was connected to 3, 1, 2, 3 carbons. Okay, yeah, that's why tertiary.
Yep. And then this side, what is this side? What?
Technically not even a primary. It's not connected to any carbons. It's just connected to the oxygen, right?
It's a methyl electrophile. Imagine if I have this. That's a methyl electrophile, right?
Oh yeah, okay, I can see that.
And this would be my leaving group. Well, right now, this could be my leaving group. Double-sided electrophile, huh?
Yep.
So this particular one is a double-sided primary, option shift 8, and tertiary option shift 8 electro. Oh, what? Didn't work. Option. Oh, I did command. Nice, right? It usually takes students a little while to connect the idea that it's a double-sided electrophile, but I think you're getting it already, which is great. So I'm going to do the tertiary one first from this guy, and then I'll redraw it for the other one. So I'll go, I don't want to do yellow. I thought I had red. I'll go, whoop. And I'll say, kind of wish I had a little more room. I'm going to start writing smaller on these jamboards. And then, is that a good leaving group? This methanol that came off? Yep, because it's a weak base. All right, and then what do I think? Rearrangement. Always think rearrangement, but will this one rearrange? No, it's happy. It's a tertiary carbocation. So our iodide's a strong nucleophile, though. It can add right in there, and we can get a product like this. Come on now. Wiggle, 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 wiggle. I'll put it down here. Wiggle, 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 wiggle. It's going to add down there. I don't want it there. Iodide, because it can add from either side of this carbocation, and it's creating a stereocenter. Okay, so one of our overall products is this. I'm going to keep these guys separate. Sorry for the mess. And I know it's redundant to like, oh, I've already drawn the product in the mechanism. Why do I have to draw it in the overall? I just like you to. It's good bookkeeping. Okay, so now I'm going to draw up the, oh, come on. I'm going to draw up the the double-sided electrophile with the good leaving group again. I'm going to redraw it. I think it's better to redraw it than to try to draw the mechanism, multiple curved arrows on the same thing. So I'm going to redraw it right here. I'm going to go. With the SN2 mechanism. So this is the redrawn. Seems weird I didn't draw the methyl out, but I was hoping you guys can follow along with that. Oh, forgot my protonation. Okay, there we go. Oh, come on.
Is that hydrogen coming off the oxygen or?
Yeah, I redrew this protonated ether.
Oh, the protonated one. Okay.
Yeah, it needs to be protonated to give you, it's a good leaving group then, right? Does that make sense now? I've got the methyl iodide product. Or maybe I'll write it up this way over here to make it more obvious. There we go. All right, we know how to cleave ethers.
Both of those going to happen, or is one going to be favored?
You know, I think both will happen. I think the tertiary side might form a carbocation faster because tertiary carbocations are the lowest energy ones to form, and it's an intramolecular step to do this. The leaving group leaves on its own, doesn't have to wait for the iodide to hit. I believe this will be the major, but I'm not going to ask you.
Okay.
I'm just going to ask you to draw them all.
Are we going to draw the alcohol also as the product on top?
Yeah. What am I doing? Thank you. I thought I was forgetting something. I've got a nice example problem similar to this one in homework. I'm going to show you real quick. I won't go over it, but I'll just verbally talk to you about it. It's the chapter 9 homework. Boom. This one, I like it. So you're doing an ether cleavage for a cyclic ether. So what's the first step of the mechanism? Protonate, because the HBr is a strong acid, it protonates. It's what it does. And then it's tertiary on both sides. So I'm gonna have to go SN1 on both sides. So let's say the bond broke on this side. That would give me the alcohol in the same S configuration. And then my bromide can come in either side of the carbocation that would form here to give me like this bromide and that bromide. So these two products would happen when that side breaks. But if that side breaks, which is just as likely, then I'd get the alcohol on the right and the bromide would be on the left, R and S. Kind of cool, huh?
Professor?
Yeah.
We did not make an E1 because iodide is a very weak base, like very, very weak base.
Very weak. Yeah, no worries about E1 with that one.
Okay.
And then, so next up, protecting groups. Yeah, we got time for some protecting groups. So this won't be on exam 1, but it'll be on exam 2, and it will, it's got very similar stuff to what we're doing right now, so it's good. All right, so what's a protecting group? Why do we need it? Let's say you want to add an organolithium to a carbonyl carbon like this, but the molecule also has a protic group on it, like an alcohol. So you want the lithium to go to the carbonyl, but you know what happens? Just about every time, it just deprotonates the alcohol. So you don't get addition to the carbonyl, and your organolithium's quenched. Now it's an alkane, ethane. It's a gas, so just bubble out, the solution's gone. So how do we get around this problem when you have something that an area of a molecule where you want it to react, but there's another area that's much more reactive with what you're adding? You have to protect it. So what we can do is we could take this guy and we can make an ether, just like a mineral acid synthesis ether. And once we've done this, we've seen that ethers, I told you already, that ethers are very stable under base conditions. So once you've made this is a protected alcohol, then you can add an organometallic to the carbonyl and it won't be reacted with by an alcohol because there's no longer an alcohol, now it's an ether. And then you get your addition you want. Oh yeah, the lithium, the organolithium, when it's in solution, when it's in either THF or ether, diethyl ether or THF, it's a very basic reagent, has a very high basicity. But ethers are stable in bases. They're not stable in acids, but they're stable in bases. So you can do that, and then later you can deprotonate deprotect the protected alcohol. So here's my protected alcohol. I had to protect to get my addition I wanted. Now I take that terpyl ether off. And you can do it by, it's interesting. Above we added sulfuric acid to get an alcohol to, protect. And now we're adding sulfuric acid to deprotect, but we're adding water. And I'll show you the mechanism for that. And let's do an example of it.
Oh, so this lets you do organometallics when you have an alcohol. Because like you mentioned a while ago when we were doing organometallics, that it would react with the alcohol group first.
Right.
So you wouldn't get what you wanted.
Mm-hmm.
But now we get, oh, this is awesome.
Yeah, cool, huh? I'll do it out loud, actually. Oh. So we want this.
Are you on the Jamboard right now?
I am. Thank you so much. So say we have this aldehyde, which also has an alcohol, and we want to add like I want to start with this, and our goal is to make the following. I'll number these so I can keep track of everything. Let's go 1, 2, 3, 4. So it's like 4, 3, 2, 1. And then I'll go A, B, C, A, B, C. So your first thought might be, oh yeah, I just need to make the organometallic out of this and add it to the aldehyde. But if I make an organometallic here, instead of going to the aldehyde, it's just going to deprotonate the alcohol. Darn it. So we got the retro is tough to do with protecting groups. So, but I'll just do it for you. And I mean, of course I'm gonna do it for you, but as you get practice with these, you'll be able to do the retro. But when you're first learning how to do these, if you're having trouble writing a retro with a protected group, just do the synthesis initially. Well, I shouldn't say that. I want you guys to get good with retros. You'll probably be good with it. Oh, come on. What? Okay, let's do the retro first. Okay. So like all retrosynthesis, you start with your final product. You just draw it up. And I see an alcohol, so I'm like, oh, disconnects, right? Let me make sure I counted this right. It should be 1, 2, 3, 4. Yep. But I know from experience that, oh yeah, I need to do a protecting group. So I'm going to say that this guy actually comes from initially, or the first step back will be the tert-butyl ether protecting group. And then I'll go from not there. Oh, what am I doing? Come on, Mark. This is your first rodeo. That's the alcohol that's protected. Okay. And then I can say, oh yeah, I can disconnect now, and I can disconnect over here, you know, between the carbon with the alcohol and one carbon away. And that can come from, say, an organolithium and the protected aldehyde. And the protected aldehyde can come from the unprotected aldehyde. I feel like I might be miscounting my carbons. Let me double check. So I got 1, 2, 3, 4. Yep. 1, 2, 3, 4. Good. 1, 2, 3, 4. Good. Oh, I drew the protected again. Okay. And then, of course, our lithium would come from bromide, which would come from just the alkane we were given. All right, our retro is done. Now for the synthesis. And the retro might seem confusing at this point. Hopefully the synthesis will help you see it. I'll make the organometallic first. So I'll start with this. Oh, you want me to show you a shortcut? I almost shouldn't show you this, because if you do this and you're not really good at synthesis, you're going to make a mistake. But what the heck, don't do this unless you're really good. You could say, I'm going to add bromine in light, and then I'm going to add reaction 2, lithium and say like diethyl ether, and I right away have my lithium all over one arrow. Because remember when we say 1, 2, we're saying 1, we run this reaction and we purify it, isolate it, get NMR, IR, make sure we made it. And then in another reaction flask 2, we do this. It's different than like a 1A, B, that's all in one flask. Okay, so let's pause there. And then the aldehyde alcohol, we're gonna protect it. So we're going to do the mineral acid ether synthesis in this case. Sulfuric acid, and we'll get the alcohol protected. Notice how I'm not writing out mechanisms in my synthesis. I like it nice and clean. If you wanted to like check your overall with this mechanism, just write it off to this another piece of paper or something. Okay, and mechanistically though, I could think about it. What happens first? This guy is protonated by the sulfuric acid. The water leaving group, good leaving group leaves. Tertiary carbocation adds, and then it gets deprotonated by this or water. Okay, I got it protected. So now I can add my organolithium. And this acidic workup is normally like just mild acid. So it won't deprotect. You could like make this more acidic to deprotect, but I think it's easier to see initially. Oh wait, what am I doing? I'm having trouble talking and writing today. Okay, oh, I wasn't even talking. Boom, 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 and then we deprotect. You could deprotect different ways, like we could try to deprotect with like HBr, you know how we just learned how to cleave ethers. But HBr would be a bad idea for this one. Do you know why?
Not SN2 favored?
No, it's because the HBr would also protonate this alcohol and it could leave or do SN2. It can get a bromide here as well. Remember, we could turn alcohols into bromides with the HBr. So we're going to do the milder, add water, sulfuric acid. So it's dilute sulfuric acid in this case. And so what will happen mechanistically is this will be protonated, then it could leave, and then the water could add to it, and then you got your 2, like that. If you keep this reaction cool, you'll get SN1, this product. But if you heat it up, you'll get, instead of that, you get E1. So you get an alkene here instead. Let's see what time we got. Oh, we got time for that probably, huh? I'll show you the mechanism for that. Does anybody have a question about this alcohol here in the presence of water and sulfuric acid? Oh, shoot. We could have problems with that.
I just had a question what you meant by being protected, because I was trying to write down, so I wasn't really paying attention to the actual thing.
So let's say I didn't do this step here. If I added the lithium directly to this aldehyde alcohol, what would happen? Can you see that mechanistically?
Oh, sorry, I was muted. Okay. So the lithium would pop off, grab the. Okay.
It would wind up not adding to the aldehyde because the alcohol is more reactive.
Okay.
So, but if I turn the alcohol into an ether, we call that protecting the alcohol. So now it won't have the alcohol reactivity.
Okay, so we're just preventing reactivity to be able to do a further reaction.
We're protecting one area of the molecule, so other areas are available to react, and that one's not.
Okay. Thank you.
Yeah, you're welcome. Let me show you this last step to the mechanism. So in this last step, we've got, let me make sure I just copy it so I know. Okay. The mechanism for this guy. So what's going on is initially, actually, since we have water and sulfuric acid, we're not even going to really have sulfuric acid. Oh. We'll have hydronium and hydrogen sulfate because sulfuric acid is a very strong acid. Like we talked about in the solubility lab, how when you have a strong acid that's in water, your strong acid doesn't really exist in that solution. It's hydronium's the acid.
Mark?
Yeah. Oh, did I not? Yeah.
Wouldn't it cause an OH to pop off as a water?
It might. Yeah, that's what I was getting at. I'm glad you noticed. That could be a problem for this guy. I'm assuming you're thinking what I'm thinking. So this is what'll lead us to the product that I drew. If this gets protonated, okay, and then the carbocation can form. Our alcohol is deprotected at this point. And we've got this carbocation. If you keep the reaction cool, then the water will do SN1, add, and then another water molecule could deprotonate it. Oh. This is the product I showed on the last panel. Okay, another thing that can happen though is when you get to that carbocation, if you have the reaction heated up, do you know what'll happen?
Would we see E1?
Yeah. So one carbon away, you'll deprotonate. And it's not necessarily a bad thing. You probably don't even care whether you get SN1 or E1, because this is the part of the protecting group you removed and you're like done with it, you know? You'll still have your alcohol that's deprotected. Okay, but now, Lewis, were you asking about this alcohol being protonated earlier?
Yeah.
Yeah, that could be a problem for this example. I didn't notice it when I wrote it up. But what happens if we protonate this guy? It makes it a good leaving group, right? And it could just come off to make a secondary carbocation, and then what could be a problem? Rearrangement. And then the water would come back. We could have the alcohol wind up being on the tertiary carbon. That could be something we don't want on this one. So this was not, again, not a perfect example, but it brought up more talk. That's okay. Okay, let me show you just one other thing really quick before we're done. On chapter 9, I go into protecting groups, and so I tell you a little bit of the more about them, but we won't use these other ones. But what I want to show you is that there are more protecting groups than just the tert-butyl protecting group we learned about. There's these silyl protecting groups like the tert-butyl diphenyl silyl ether. This is a real popular one. And tert-butyl dimethyl silyl ether. These ones are really nice. They're actually, these are used more often than the tert-butyl, but I teach you the tert-butyl because it's related to SN1 and it's kind of the foundation. These ones are really nice because they go on nice, easy, and they come off easy because you can add just fluoride ion, and fluoride makes arguably the strongest single bond with silicon, so it comes off easily. The guy who invented it is E.J. Corey. He's kind of the Michael Jordan of organic chemistry. He's a Lebanese American. I think he was first generation. I think his parents are from Lebanon, maybe, or is he born? I don't think he was. I think he was born on the East Coast, but he's, yeah. And so he's like come up with amazing stuff, protecting groups being one of them, and retrosynthesis. He was the one who popularized retrosynthesis. And he, another, you know, great kind of immigrant story of the USA. And also these protecting groups, all the different ones, we're only going to do tert-butyl ethers. They have like these tables that show you, oh, if it's really acidic, it comes off. If it's basic, it's all good. Like lithium aluminum hydride, strong base, organolithium, strong base. It's stable in these conditions, but it comes off under these conditions. So you can see, like I said, the silyl protecting groups, they come off with fluoride. Do they have, I guess they don't list it in the table, but yeah. Yeah, so protecting groups are a big part of organic chemistry. Show you one more thing. Let's see, I'll go to PDFs. Sorry, this one's a nice one. Okay, so check it out. Here is a journal article. Like we've been learning, this is an organic synthesis publication. Oh my God. And what do we have here? They're making this particular molecule, bornolide, and they're showing you, okay, we made it. And then so these kind of publications, they just start off with like, why are you making it? And like, oh, there's a functional group moiety or to this that it tends to have biological activities such as like antimicrobial and stuff like that. Insect growth inhibition, anti-tumor, antibacterial, blah, blah, blah. So how do they do this? They start off with retrosynthesis. This is their final product. So this, I don't like that they use this arrow. I like to clear out that last part, make it the double lined arrow. But they're doing retrosynthesis, saying I can make this from this, and I can make this from this, and going back to like a simple molecule that's cheap to buy. And then they go through and they tell you about the synthesis. So they start off with an aldehyde, they make it into an ester. And then these R groups, check it out. They're alcohols to begin with. And then they make them into this isopropylidine. That's a protecting group. And then they use the MOM, methoxymethyl ether protecting group. So these are different protecting groups they've tried, and a benzyl protecting group. They didn't use the tert-butyl one we talked about, but you can see they're using protecting groups in this because they need to like protect these. They need to protect these two alcohols to change the ester here. And now you have an alcohol that's not protected, where these two are still. So you can oxidize just that alcohol to the aldehyde, keeping those protected, and then at the end you can deprotect them. Got all the different conditions. So this is pretty high-end stuff, and now you guys can kind of understand it, huh? You've got this is an alcohol protected as a MOM protecting group, and this is a tert-butyl diphenyl silyl ether protecting group, MOM protecting group. So you can use fluoride to take off just this tert-butyl diphenyl silyl ether protecting group, and the MOM will stay on. And you can react. So yeah. So it's pretty cool. You guys in August, you would look at this and have no idea, but now you're getting kind of an idea about it. Look, got all this NMR stuff. Oh, the carbon NMR, 200 megahertz. That article I just showed you, I kind of went over it fast, but if you even gleaned a little bit of what was going on, you're a very special, small portion of the human population, because Most people on Earth would have no idea what any of that meant, and now you're kind of starting to get it. Pretty cool.